Hello everyone and welcome to Dr. Rajesh Biogenesis. In this video, let's discuss about one of the symmetry elements that we have. The first one, proper axis of symmetry. It is generally abbreviated as POS, or we can also call it as rotational axis of symmetry. Whether it is a symmetry element or symmetry operation, they are intricately related to one another. So whether it is simply a proper axis or taking into consideration the operation called as rotation, you can also call it as rotational axis of symmetry. What exactly is the angle of rotation so that we get a valid rotational operation? What are different stereographs? Everything has been explained in one of the videos. You can just go through that. I'll just extend some of the examples. So before getting into more examples, let me give you a couple of more points. When I explain about a rotational axis, you have to remember that every symmetry element is purely imaginary, and every symmetry element must pass through the center of gravity of the molecule, which we commonly call as the center of the molecule. Whatever operation that we perform, such an operation must be a valid operation. For example, if I choose water molecule, supposing that this is a molecular model for water, oxygen and 2 hydrogens. If I try to pass a rotational axis through y, remember the conventional axes are x, y and z. So suppose that I am passing a rotational axis along y, and if I am trying to rotate by 180 degree, the 2 hydrogens which were below, now they are coming above. So this is not a valid rotational operation. Or just let me pass it through x. The 2 hydrogens are below, and as I rotate by 180, now these 2 hydrogens are going above. This is also an invalid operation. But when I pass the rotational axis through z coordinate, and as I rotate by 180, it is giving an indistinguishable configuration, which you call it as a equivalent configuration. Hence only this rotation along 180 degree is possible. This is a valid rotational operation. So every rotational axis, either it is from x, y or z, is passing through the center, but only one of them is valid, and we have to consider only the valid rotational operations. Okay, to that point we have to take only the valid operations. Let it be a rotation, reflection, inversion, only the valid operations must be considered. I discussed all the details about water molecule in the previous video related to rotational axis. I'll just try to extend it. Now, just as a refreshing example, I am just choosing a water molecule. Within this water molecule, this is the rotational axis. There is a C2 rotational axis, and conventionally we can rotate in a clockwise manner. Counterclockwise manner is also allowed, but the convention is generally we follow clockwise rotation. As I rotate, these are 1 and 2 hydrogen atoms. They get exchanged, and when I don't number them as 1 and 2, it is just like 2 hydrogens below, 1 oxygen above. They are just looking the same. In fact, they are not the same, they are similar ones. So for this reason, I have to perform one more rotational operation. I have to rotate by 180 degree. That is a C2 rotation, and that will provide an identical configuration. So 1 is at a position of 1, we say it is a identical configuration. The first and the last structures will be identical. In between whatever structures are generated, that will be an equivalent structure. Or whatever pair of molecules that you choose, pair of molecules in the sense whatever pair of configurations that you choose, only one pair will be called as an identical pair, the first and the last. Any other combination would be equivalent pair. If I consider this as structure 1, 2 and 3, 1 and 2 are equivalent pair, 2 and 3 are equivalent pair, but the first and last is always an identical pair. This is what we have learnt in the last video of rotational axis. After H2O, now let me choose another simple molecule. Only when we discuss a few examples, you can understand the concept much better. Let me choose ammonia. I draw ammonia this way and I just try to pass the rotational axis. That may look difficult for some students. So for convenience, let us put ammonia in a different way. Hold ammonia in such a way that all the three hydrogens are facing towards you or they are facing away from you. That is a convenient way to understand the symmetry elements. All these symmetry elements are just for our convenience so that we can understand the patterns present in a molecule. Now this is how the first orientation is. There is a lone pair and these are the three hydrogens, nitrogen at the center. Instead of holding ammonia in this way, you can just imagine, try to hold the ammonia in this manner where the three hydrogens are facing towards you or the three hydrogens could face away from you. As I hold the molecule in this way, ammonia looks a pyramidal molecule. It is not a planar molecule, it is a pyramidal molecule. There is a C3 rotational axis. Whenever a molecule is given, the strategy is to identify the relation between the ligands. Once you identify the relation between the ligands or the bonded atoms, very easily you can establish the rotational axis. There is a triangle relation of an identical atom. And whenever you find a triangle relation of an identical atom, there is a choice or there is a chance for a C3 rotational axis. I just don't say that every time there will be a C3. That depends on the type of molecule. But wherever you find a triangular relation of identical atoms, there could be a C3 possibility. Then you have to try. So that C3 rotational axis is towards you. And when I rotate by 120, it is giving an equivalent structure. Rotate by another 120, equivalent structure. Third 120 is an identical structure. With this we confirm that in ammonia there is a C3 rotational axis. Every time I will not put all the orientations, you can understand that. There is a C3 rotational axis in ammonia which is pointing towards you when this is the orientation of ammonia. C3 will generate C3-1, C3-2 and C3-3. So when I have rotated 3 times, I got a identical structure. What is the fold or how many times I have to rotate to get an identical structure, or what is the periodicity to get it? Let me take n here. N is periodicity or fold. We are rotating by 120 degrees so that we get an equivalent structure. And the periodicity or the repetitions are altogether 3. When I rotate 3 times, I will get an identical structure. So this is for ammonia. For water molecule, when I rotate 2 times, I am getting an identical structure. For ammonia, when I rotate 3 times, I am getting an identical structure. I can also rotate 10 times. I am just taking an ammonia. I can also rotate 10 times. I can rotate 20 times. But it is not how many times we are rotating. It is just how many valid configurations that we are getting in this rotation. So as I am rotating, now this is a valid operation. Second time is a valid operation, that is 120 degree. Third is a 120 degree valid operation. If I try to rotate by some angle which is invalid, you should not consider such a rotation. So only 3 rotations are valid. That is the reason we put periodicity or fold is 3 for ammonia. Apart from C3, you don't find any other rotational axis in this. Well, after ammonia, let me choose another simplest of the molecules, Bcl3. I'll just take a couple of molecules so that you'll understand what are the different types of rotational axes that are present. Bcl3 looks similar to ammonia, but this is a planar molecule. This is a Bcl3 molecule. Now this looks planar. It is not pyramidal. There is again a triangular relation of identical atoms. Therefore, you can expect a C3. and when you try to rotate by 120 degree, that will give you an equivalent orientation or equivalent configuration. So we say that there is a C3 rotational axis in Bcl3. That C3 is present and it is passing through the boron, and when you rotate by 120 degree, that will produce a equivalent orientation. Apart from C3, Bcl3 also has other rotational axes. What are these? You can just watch. Suppose if I am holding Bcl3, this is a C2 that is passing from one of the chlorines and the central boron atom, and as I rotate by 180 degree, it is giving an equivalent configuration. You can just check. Okay. There is a C2 which is passing from one of the chlorines. In a similar way, there is one more C2, there is one more C2. So altogether there is a C3 rotational axis. Also there are C2 rotational axes. Altogether there are three C2s and one C3. I will just represent these C2s. From whichever atom the rotational axis pass from, they remain. They do not shift or they do not exchange their position, but the other atoms will exchange. Supposing that this is one C2, this is a second C2, and this is a third C2. In Bcl3, there is a C3 rotational axis. Also there are three C2s. So I am just concluding it. One C3 is present plus 3 C2s. This will be interesting. When I take another example, slowly the concept will become interesting. Suppose that I am taking ethylene as an example, then you can identify the rotational axis present in ethylene. I will be showing you the molecular model. You just try to visualize the symmetry elements present in them. This is the molecular model for ethylene. 2 carbon atoms, 4 hydrogens. There are 2 CH2 units that are eclipsed to one another. You may hold it in any of the convenient orientations. Either I can hold ethylene in this manner, or I may hold it this way, or I may hold it in this way. Supposing that I am holding in this manner, in this particular orientation of a YZ plane, XZ, YZ, XY, 3 different planes. I am holding it in a YZ plane. You can see that there is a C2 rotational axis passing through 2 carbon atoms, and as I rotate by 180, it is providing an equivalent configuration. Okay. I am also showing it from this orientation. I am passing a C2 that is passing through 2 carbons, and as I rotate by 180 degree, it is providing an equivalent configuration. So we say that there is a C2 rotational axis passing through the carbons. Apart from this, I can also pass a C2 along this axis. I rotate by 180, it is providing equivalent configuration. Let me pass it through this. I rotate by 180. This is also providing an equivalent configuration. So what do I conclude? If I choose ethylene molecule, in ethylene altogether there are C2s 3 in number. Now you can imagine yourself to be present in this planet. You are alone on this planet. No one else is present on this planet. Then you don't need any name for you, because no one has to call you. Until and unless you feel that you call yourself, you don't need any name. But suppose there is a second or a third person on this planet. Then they want to call you. You need a name, because you have to call them, they have to call you. Therefore you should have some different names. In a similar way, Whenever there is more than one rotational axis, we have to name them, and for naming them we have some guidelines. If you can just follow that guideline, very easily you can say what is the type of rotational axis. Now I am showing you three different types of rotational axis. How do the atoms shift is more important for you. Where do the atoms go? One need a lot of patience to understand symmetry, apply it to many number of molecules. Now this is a rotation which is a out of plane rotation. So the hydrogens that are present below will be exchanged by the hydrogens that are present above. 1 and 2 will get exchanged, 3 and 4 will get exchanged. Just let me write that pair. 1 and 2 are getting exchanged, 3 and 4 are getting exchanged. It is an equivalent configuration but not an identical one, because the position of the hydrogens has been shifted. But every position of a hydrogen is taken up by another hydrogen. Therefore, we call it as an equivalent configuration or an equivalent orientation. In the second case, the right and left hydrogens are getting exchanged. In the first case, below and above hydrogens are getting exchanged. In the second case, right and left hydrogens are getting exchanged. This is also an out of plane rotation. So 1 will exchange with 4 and 2 will exchange with 3. In the last case, that is a rotation which is called as a in-plane rotation. This is a in-plane rotation, and within this in-plane rotation 4 and 2 are related by 180 degree. 1 and 3 are related by 180 degree. Therefore, these two hydrogens exchange and these two hydrogens exchange. And these are again equivalent structures. If I perform another C2, that will produce an identical structure. I need not do it, you can understand. Altogether we can say that there are 3 C2s. Now coming to the most interesting point. Forget about water molecule, try to consider Bcl3 and ethylene molecule. This is an example of ethylene, right? If I consider even the water molecule, there is only one rotational axis in it. When I come to Bcl3, there are 4 rotational axes. One of them is a C3, the others are C2s, and all these C2s you can see that they are perpendicular to the C3. Then coming to an ethylene, there are multiple rotational axes and all of them are just the same, C2, C2 and C2. Now comes the most important point with respect to proper axis or rotational axis of symmetry. Whenever there is more than one rotational axis, then we have to differentiate them. First guideline is, whenever there is more than one rotational axis of different order is one is 3, the another one is 2. So the guidelines say, whenever there is more than one rotational axis of different order, that rotational axis having a higher order will be called as a principal axis. The remaining will be subsidiary or auxiliary or secondary axis. If I follow the same guideline for ethylene, then it will go wrong, because in ethylene there are multiple rotational axes and all of them have the same order, the order of 2. So for this reason, what we say is we have to use a second guideline. First guideline I am repeating, whenever there is more than one rotational axis of different order, higher order will be the principal axis, C3 is the principal axis, remaining are subsidiary or secondary. When I choose ethylene type of molecules where there is more than one rotational axis but all of them have same order, in such a case that rotational axis which pass from more number of atoms must be called as a principal axis. The remaining perpendicular C2s or the remaining rotational axis will be subsidiary. So in this case, the first one I can call it as a principal axis. The remaining 2 are subsidiary to it. Okay. If you can remember these two guidelines, it will be very easy to identify which is the principal axis and which is the subsidiary axis. Finally, I am just showing you ethylene. This is alene. I have shown you ethylene. Now this is a molecular model for alene. The difference is addition of one carbon unit, there is another carbon atom that is being added in the center. Main difference is there is a CH2 and a CH2 unit that are staggered to one another, but in this case the two CH2 units are eclipsed to one another. There are 3 C2s in it, also there are 3 C2s in it. There is a principal axis and subsidiary axis. For allene, I have represented all the symmetry elements in a video, you can just go through that video. There is a C2 which is passing from 3 carbons and 2 C2s which are perpendicular to this and are passing from the central carbon atom. So the one which is passing through 3 carbon atoms can be called as a principal axis, and the other 2 C2s which are perpendicular to it and it is passing only from the central carbon atom are called as subsidiary or secondary axis. So this is how you have to identify the rotational axis present in different molecules. Thank you.